We continue our lecture on functions with figure 5b. 5b is onto, but not one-to-one. It's not one-to-one because we have two elements in the domain that map to one element in the codomain, and every element in the codomain can be mapped to an element in the domain. Figure 5D is neither one-to-one nor onto. It's not one-to-one because elements A and C map to a single element in the codomain. And it's not onto because element 4 is not mapped back to the domain. And then figure 5E is not a function because we have element A is mapped to two elements in the codomain. Example 12. Let f be a function from ABC to 1, 2, 3 by f of A equal 3, f of B equal 2, f of C equal 1, and f of D equal 3. Is f an onto function? Solution: because all three elements of the codomain are images of elements in the domain, we see that f is onto. This is illustrated in the figure below. Notice that if the codomain were 1, 2, 3, 4, f would not be onto. Example 13. Is the function f of x squared from the set of integers to the set of integers onto? Solution: the function f of x is not onto because there's no integer x with x squared equal minus 1. Example 14. Is the function f of x equal x plus 1 from the set of integers to the set of integers onto? Solution: the function is onto because for every integer y, there is an integer x such that f of x equal y. To see this, note that f of x equal y if and only if x plus 1 equal y, which holds if and only if x equal y minus 1. Example 15. Consider the function f in example 11 that assigns jobs to workers. The function f is onto if for every job there is a worker assigned a job. The function f is not onto when there is at least one job that has no worker assigned to it. Definition 8. The function f is a one-to-one correspondence or a bijection if it is both one-to-one and onto. Example 16. Let f be the function from ABC to 1, 2, 3, 4 with f of A equal 4, f of B equal 2, f of C equal 1, and f of D equal 3. Is f a bijection? The function is one-to-one and onto. It is one-to-one because no two values in the domain are assigned the same function value. It is onto because all four elements of the codomain are images of elements in the domain. Hence, f is a bijection. We see a graphical representation of f in the diagram above. A function is a one-to-one and onto if it can be inverted. The function can be inverted if all the directed edges can be reversed and all the elements in the codomain are mapped to by the reverse directed edges to individual elements in the domain. Example 17. Let A be a set. The identity function on A is the function I subscript A maps from A to A, where I subscript A of x is equal to x for all x an element of A. In other words, the identity function for A is the function that assigns each element to itself. The function I subscript A is one-to-one and onto, so it is a bijection. Inverse functions and compositions of functions. Definition 9. Let f be a one-to-one correspondence from the set A to the set B. The inverse function of f is the function that assigns to an element B belonging to set B the unique element A in set A such that f of A equal B. The inverse function is denoted by f inverse. Hence, f inverse of B equal A, where f of A equal B. Example 18. Let f be a function for ABC to 1, 2, 3 such that f of A equal 2, f of B equal 3, f of C equal 1. Is f invertible? And if it is, what is if it's inverse? Solution: the function f is invertible because it is a one-to-one correspondence. The inverse function f inverse reverses the correspondence so that f inverse of 1 equals c, f inverse of 2 equal a, and f inverse of 3 equal b. Example 19. Let f be a function from the integers to the integers such that f of x is equal to x plus 1. Is f invertible, and if it is, what is its inverse? The function f has an inverse because it is a one-to-one correspondence, as has been shown previously. To reverse the correspondence, suppose that y is the image of x, so that y is equal to x plus 1. Then x is equal to y minus 1. This means that y minus 1 is the unique element of the integers that is sent to y by f. Consequently, f inverse of y is equal to y minus 1. Example 20. Let f be the function from the reals to the reals with f of x equal x squared. Is f invertible? Solution. Because f of 2 equal f of minus 2 equal 4, f is not one-to-one. If an inverse function were defined, it would have to assign 2 elements to 4. Hence, f is not invertible. Example 21. Show that if we restrict the function f of x squared to non-negative real numbers, then is f invertible? Solution. One-to-one. The function f of x equal x squared from the set of non-negative real numbers to the set of non-negative real ones is one-to-one. To see this, note that f of x equal f of y, that if f of x equal f of y, then x squared equal y squared. So x squared minus y squared equals 0. X squared minus y squared can be factored to x plus y times x minus y equals 0. That means x plus y is equal to 0 or x minus y equals 0. So x equal minus y or x equal y. Because both x and y are non-negative, we must have x equal y. So this function is one-to-one. Onto. Furthermore, f of x equal x squared is onto when the codomain is the set of all non-negative real numbers, because each non-negative real number has a square root. That is, if y is a non-negative real number, there exists a non-negative real number x such that x is equal to the square root of y, which means that x squared equal y. Invertible. Because the function f of x equal x squared from the set of non-negative real numbers to the set of non-negative real numbers is one-to-one and onto, it is invertible. Its inverse is given by the rule f inverse of y is equal to the square root of y. Definition 10. Let g be the function from the set A to the set B, and let f be the function from the set B to the set C. The composition of the functions f and g is denoted for all elements A that are elements of the set A by f composition g, defined by f composition g of A is equal to f of g of A. Example 22. Let g be the function from the set ABC to itself such that g of A equal B, g of B equal C, and g of C equal A. Let f be the function from the set A, BC to the set 1, 2, 3 such that f of A equal 3, f of B equal 2, and f of C equal 1. What is the composition of f and g, and what are the composition of g and f? Solution. The composition of f and g is defined by f of g of A is equal to f of B equal 2, f of g of B is equal to f of g of B is equal to f of C equal 1, and f of g of C is equal to 3. Example 23. Let f and g be the functions from the set of integers to the set of integers defined by f of x is equal to 2x plus 3 and g of x is equal to 3x plus 2. What is the composition of f and g? What is the composition of g and f? F of g of x is equal to f of g of x is equal to f of 3x plus 2 is equal to 2 times the quantity 3x plus 2 plus 3, or 6x plus 7. G of f of x is equal to g of the quantity 2x plus 3 is equal to 3 times 2x plus 3 plus 2 is equal to 6x plus 11. Note that even though f of g and g of F composition G and G composition F are defined for functions f and g in examples 21. F composition G and G composition F are not equal. In other words, the commutative law does not hold for the composition of functions. Inverse functions. When the composition of a function and its inverse is formed in either order, an identity function is obtained. To see this, suppose that f is a one-to-one correspondence from the set A to the set B. Then the inverse function f inverse exists and is a one-to-one correspondence from B to A. The inverse function reverses the correspondence of the original function, so f inverse B equals A when f of A equal B, and f of A equal B when f inverse B equals A. Hence, f inverse composition f of A is equal to f inverse of f of A is equal to f inverse of B is equal to A. And f composition f inverse of B is equal to f of f inverse of B is equal to f of A is equal to B. Graphs of functions. Let f be a function from the set A to the set B. The graph of the function is the set of ordered pairs A, B, where A is an element of set A and f of A is equal to B. Display the graph of the function f of n is equal to 2n plus 1 from the set of integers to the set of integers. Solution. The graph f is the set of ordered pairs of the form n, 2n plus 1, where n is an integer. The graph is displayed below. Example 5. Display the graph of the function f of x equal x squared from the set of integers to the set of integers. Solution. The graph of f is the set of ordered pairs of the form x, f of x equal x squared, where x is an integer. The graph is displayed here in figure 9. Some important functions. The floor function assigns to the real number x the largest integer that is less than or equal to x. The value of the floor function at x is denoted the floor of x. The ceiling function assigns to the real number x the smallest integer that is greater than or equal to x. The value of the ceiling function x is denoted by the ceiling function. We can see here in figure 8 a graph of the floor function, and in 8b a graph of the ceiling function. Example 26. These are some values of the floor and ceiling functions. The floor of 1/2 is 0, the ceiling of 1/2 is 1, the floor of -1/2 is -1, the ceiling of -1/2 is 0, the floor of 3.1 is 3, and the ceiling of 3.1 is 4, the floor of 7 is 7, and the ceiling of 7 is 7. Example 27. Data stored on a computer disk or transmitted over a data network are usually represented as a string of bytes. Each byte is made up of 8 bits. How many bytes are required to encode 100 bits of data? Solution. To determine the number of bytes needed, we determine the smallest integer that is at least as large as the quotient when 100 is divided by 8, the number of bits in a byte. Consequently, the ceiling of 100 divided by 8 is the ceiling of 12.5 is 13 bytes. And so 13 bytes are required. Here are some exercises.